Swayamprabha. Digital India. Educated India.
Greetings, welcome again to this course on CFD. This week we will talk about an important subject called turbulent flows. Syllabus for this week: Introduction to turbulent flows. We derive governing equation for turbulent flows. We define a term called Reynolds stress and how to do modeling for Reynolds stresses. Then we have variety of turbulence model. We will talk about standard turbulence model, their different variants and explanation about their performance. We will also talk in detail about another class of model, what is known as low RE models. Most of the flows encountered in engineering applications are turbulent in nature. For example, flow through turbine, flow past buildings, automobiles, aircraft or any other structure, flow in a channels, jets, etc. You can also observe agarbatti smoke or cigarette smoke, the origin and then diffusion or the spreading of the smoke. This is also due to what is known as a turbulence characteristics of that flow. We also have a separate branch called atmospheric turbulence, ocean turbulence, etc. So, turbulence exists in all branches of engineering. At very low RE, flows are usually considered to be laminar, whereas at high enough RE, it becomes turbulent. In the case of laminar flow, it is a very steady flow, very organized flow, and it is possible to use Navier-Stokes equation or any other form of Navier-Stokes equation can be used. In very simple situation, it is also possible to obtain analytical solution for laminar flows. In other situation, it can be solved numerically without any further treatment in equations. Whereas for turbulent flows, we will see later what are the characteristics. Because of its nature, it needs modification in the equation and special treatments before turbulence model can be applied to engineering problems. Let us start defining the turbulent flow. It is unsteady, so you do not have anything like unsteady term dropped in Navier-Stokes equation. It is irregular, so you do not have any predefined situation, non-periodic motion. We are worried about or we are concerned about three properties: mass, momentum and scalar species. It may be temperature, it may be density, it may be concentration. So, in turbulent flows, these quantities are transported and they exhibit fluctuation both in time as well as in space. Hence, it becomes three dimensional. So, we learned three important property: one is unsteady, irregular and three dimensional. You can have a situation of laminar flow unsteady, but it will not have a it need not have a three dimensionality in the flow. Because of this, there is a very good mixing of mass, momentum as well as energy. For example, you take coffee and you add sugar, and to get fast mixing you stir it with a spoon or stirrer, then sugar get mixed quickly, and this is example of turbulent flow mixing. Similarly, as I mentioned before, the cigarette smoke or agarbatti smoke, the spreading by the process diffusion gets faster because of the turbulent flow. And you take a bucket of water, you drop a ink, it goes by itself by laminar flow, but if you stir it, then it goes faster, the spreading is faster because of turbulent action. Fluid properties and velocities exhibit random variation. Though they exhibit random variation, it is possible to apply statistical tools. One can obtain average, RMS or fluctuations squares. So, statistical averaging results in accountable turbulence related transport mechanism, and because of this it is possible to do what is known as a turbulence modeling, which is a subject for this week. It contains wide range of turbulent eddy sizes. So, when we talk about turbulent flow, we talk about spectrum. When we say spectrum, there is a range. We look for three information, that is velocity, time and length. If you look for any two, the third one you can get, that is from velocity and length you can get time, or from velocity and time you can get length information. So, in a flow you look for any two of these information, and then you can obtain the third information by the dimensional and argument. So, when you say spectrum, for example velocity information will have as small as possible to as high as possible. Similarly, when you say length information, the eddy sizes can be as small as possible to as high as possible. The eddies are fluid masses and they undergo motion. Whenever it undergoes a motion, it covers some length in the flow, and there is a turnover time, and that is what will give you the time information. So, velocity, length and time related to eddy sizes, it can be as small as possible to as high as possible. There is a wide range available in a turbulent flow, and this is what is known as a spectrum, and they exhibit range of values. The size and velocity of the large eddies is of the order of the mean flow. So, for example, if you consider flow through a circular cross section pipe, then largest eddy possible size is the diameter of the pipe itself. Then there is a process called energy cascading. I am going to explain that in the next slide with the help of a sketch. So, large eddies derive energy from mean flow, they in turn pass it to next small size, they in turn breed to the next smallest size, and it goes. Finally, at the smallest size it get dissipated by viscous action. So, energy is transferred from larger eddies to immediate smaller eddies, and then the cycle, then immediate smaller eddies, and it ends at the smallest eddies possible. This process is called energy cascading process. In the smallest eddies, turbulent energy is converted into internal energy by viscous dissipation process. This figure is an illustration to explain the energy cascade process. As you can see here, these are all largest eddies possible in a flow, and there is an arrow to indicate that eddies are in the motion with some angular velocity. Whenever an eddy comes back to its position, then you call that as a time, or whenever it moves to the next position, you call that is a length information for that particular eddy. So, in this process, energy cascading process, largest eddy transfer energy from itself to the next smaller eddy, then they in turn transfer energy to the next immediate smaller eddy, and this stage goes until the smallest possible, that is what is shown at the bottom as I am showing here, where the energy get dissipated because of the viscosity action. So, in a Navier-Stokes equation you have a viscous diffusion term, and that actually plays role here. Now, what is the responsible mechanism for the transfer of energy from one eddy to the next eddy is by what is known as the instability process, and this instability is created by inertial component in the Navier-Stokes equation, which is convection term. This figure is from a book on turbulence by Davidson. To get some more idea into the definition of turbulent flow, I am showing here an illustration which is flow through a pipe. There is a red color profile which is a mean velocity profile. So, we will learn what is mean in subsequent lectures. Now, this portion alone is zoomed and it is shown here. So, you can see clearly the red line profile, that is a mean velocity profile. Then you see wild variation, and these variations are shown with the two different colors. So, the mean is denoted by U subscript I, and there is a bar, and in the bracket you have x in bold letter comma t. Now, let us understand what is the symbol. So, I subscript stands for tensor notation. In the next lecture, I am going to talk about tensor notation and some algebra associated with the tensor notation. Then bar stands for average, and then x bold stands for to represent in which direction, that is vectorial component. Then t stands for time. So, this u velocity profile, it is a function of both space as well as time. That is the meaning of writing x comma t. Now, the mean is only one, but you are seeing two different colors to represent the fluctuations, and you can see here to represent fluctuation with respect to the mean. Now, the fluctuation is a function of time, that is why you get at one instant one fluctuation that is shown in one color, and in some other instant it will have some other fluctuation or deviation from the mean which is shown by another color. Now, the deviation from the mean is represented by prime quantity, because we are talking about velocity in I. So, it is u I prime and x comma t. So, fluctuation is a function of both space as well as time, and that is what is shown here with the notation x comma t. We explained just before that turbulent flow exhibits three dimensionality, that is it is a function of both space as well as time, and you are able to understand with the help of this velocity profile. And this is another example. This is a velocity signal that is captured by an instrument in a jet flow at one particular x location. So, you get any property f for any property that is marked on the y axis, and t for time instant, and you see one horizontal line to represent its average, and if you take the signal and plot as a function of time, you get such a wide variation. For example, if you open a tap and you get jet coming out, at center of the jet if you insert any velocity pickup instrument and you record that signal, this is how it will appear. This is another example to understand what is a turbulent flow. So, this is a representation for flow past a building. Here the building is considered to be a three dimensional geometry. Flow is from left to right, it will flow around as well as it will flow over. Now, if you observe immediate downstream, here these are lines to represent shear layer shedding and vortices shed from the geometry, and if you go slightly far enough, then you see the motion, it becomes turbulent. So, flow around building gives rise to what is known as a turbulent wake. So, wake is a region of the flow immediately behind the geometry. So, in this case the geometry is building and this is a wake region. So, the wake becomes turbulent. This is important. So, we have already mentioned turbulent flows exist in all walks of engineering. in the case of building aerodynamics also there is a turbulent flow. What we are seeing is just a representation in terms of isolated building, but in a urbanized setup you have buildings of various heights and immediately located adjacent to each other. There is a need to study flow around through building. Here you have an illustration to understand, though it is turbulent, how it behaves for two different Reynolds number. There are two pictures shown. This is turbulent jets at two different RE. On the left Reynolds number is 5000, on the right Reynolds number is 50,000. Difference between them is one order of magnitude. Jet is issued from the bottom as I am showing here, the same situation on the other side. Now you can get Reynolds number differently either by increasing the velocity at the source or changing the geometric dimension at the source. Now immediately after the exit there is no problem, flow appears to be laminar in both the situation, but as you move downstream, so if you go a little far either here or here at the same location for both situation, you see different structure for two different Reynolds number. We will have a close look at one region in the next slide. So the same jet, we take one small portion and zoom, try to understand how a turbulent flow actually for two different Reynolds number. The bottom one is for the modest RE and the top one is for the high RE. The flow appears to be from left to right. Now in each figure you have a big arrow marked and you also have a small curly lines marked. Big arrow that is marked to represent large eddy motion. We already mentioned large eddy is limited by geometric dimension of the flow. In this case the jet, once the jet is issued, the geometric dimension is actually the spread. So in this case for example from this side to this side, this is a geometric dimension, the spread, that is a limitation. The large eddy will move between this limit and that is a motion that is possible. So both in this case as well as in this case the large eddy is almost the same, whereas if you look at the small curvy lines, what you see on the top which is for the high RE, you see many small curvy lines and these curvy lines sizes are smaller than what you will see in the modest RE. So modest RE also shows curvy lines and these curvy lines represent small eddy motion and the smallest eddy is marked by the smallest curvy lines. So the information from this sketch is, as you increase the Reynolds number, the large eddy size is almost unaffected, whereas the smallest eddy that is possible becomes smaller and smaller as you go on increase the Reynolds number. You can observe once again at modest RE the curvy lines which are to represent smaller eddy are only or having a definite length, but the same curvy line becomes smaller when you increase the Reynolds number from modest RE to high RE. And this is very important because when you model turbulent flows later you have to know what is the smallest mesh size that you have to describe, because the smallest mesh size captures the smallest eddy size motion and the prediction becomes better. So I repeat, as you increase the Reynolds number, the size of the smallest eddy becomes smaller and smaller, and that puts a limitation or careful choice of the smallest mesh size that is possible. Now flows can be characterized by the Reynolds number, we already know, and in Reynolds number definition what is shown here, rho UL by mu, one has to carefully interpret what is U and what is L. U is a velocity scale and L is the length scale. So for example, flow through a circular cross section pipe, the well known example, if you consider velocity scale U, It can be a center line velocity or it can be average velocity, bulk velocity. Similarly, if you consider L length, for example, if you consider flow past a flat plate, the distance from the origin can be a length. If you consider smoke spreading from a cigarette or from agarbatti butt, from agarbatti stick, then distance from that origin wherever you are, that becomes a length. So, the Reynolds number definition, we know it is ratio of inertial force to the viscous force. After substituting formula for inertial force and viscous force, you finally arrive at this formula. So, we have to carefully interpret U and L. U stands for velocity scale, L stands for length scale. That is why you see here length, it can be x, which is the distance from the leading edge or from the source. It can be diameter of the pipe or it can be hydraulic diameter of the pipe. Depending on the definition of U and L, for the same flow you can have a different Reynolds number and you have to carefully use the subscript. So, in this case, for example, L is used, then you write Re subscript L. So, we have two situations commonly encountered, either external flow or internal flow. So, external flow, for example, flow past a flat plate, flow over an aerofoil, flow past a cube, obstacle, buildings, etc. And for flow along a surface, we define length scale L as the distance from the origin or the source, and that is why you write Rex. Now, that flow becomes a turbulent if the Reynolds number defined based on the distance greater than or equal to 500,000. Next situation, flow past an obstacle or a building or a square cylinder surface, etc. Then the Reynolds number is defined accordingly, the dimension. For example, if it is a building, it can be a cross section or it can be height, you have to define accordingly. Then Red, if it is greater than or about 20,000, then the flow can be characterized as a turbulent flow. Next situation is an internal flow, well known example, flow through circular cross section pipe. It can be any cross section, it can be a sudden convergent section or it can be a enlarging section. So, Reynolds number is defined based on hydraulic diameter, and if that value happens to be greater than or equal to 2300, then the flow becomes turbulent. Now, these values are only a guideline, they need not be same at all situations. They are also functions of what is known as a free stream turbulence, surface condition. For example, if you consider flow through a circular cross section pipe, we assume the internal walls are perfectly smooth. It is possible to have roughness introduced on the walls, then the surface condition changes. The roughness is supposed to roughness plays the role of enhancing the turbulence. So, for the same geometry, for the same velocity scale, for the same length scale, if you have introduced roughness, then the flow may become turbulent even before what is defined here as a 2300. Similarly, any disturbance upstream created, any disturbance may cause transition to turbulence even at lower Reynolds number. Now, we look at little more detail. We already mentioned, though flow exhibits randomness, it is possible to approach a turbulent flow by what is known as statistical methods, and one such quantity is averaging, because we mentioned it is varying both in space as well as time. It is possible to do both spatial averaging as well as time averaging. For now, we will limit it to only time averaging and explain turbulent flow with the help of only time averaging quantity. So, time averaging is usually used to extract the mean flow from instantaneous ones. So, any quantity that is varying with the time, we refer it as instantaneous. Once we do time averaging, then we get a mean quantity. If you subtract one from the other, then you get fluctuation. In other words, the instantaneous quantity u, for example, and we have used subscript I to represent it is in one direction or it is a tensor quantity. Ui is split or decomposed into average as well as fluctuating component. We already learned with the help of this figure. So, this is a figure for flow through a pipe and velocity profile is marked with the red color, and we take a one small portion, zoom and see the velocity profile. We already mentioned we have u bar x comma t, and that is shown here as a mean velocity profile, and you have fluctuations. There are two fluctuations marked just to understand that you get different signal for different time level, and the deviation from the mean is marked by prime. So, in this case it is ui prime x comma t. So, you can put them together and that will give you the instantaneous quantity, and that is what is shown in the expression here. Ui x comma t equal to ui bar x comma t plus ui prime x comma t, where ui is an instantaneous component, ui bar is a time average component, ui prime is a fluctuating component. We are explaining all this with the help of one quantity, that is velocity. If you are involved with the temperature, density or any concentration, each one of them can be represented in the same way, that is decomposition. Instantaneous quantity equal to mean plus average, instantaneous quantity is equal to mean plus deviation from the mean or the fluctuation. Now, before going into further details, let us have some information about tensor, notation and some algebra. I would like to caution here, whatever I am doing in this course is only very limited, and reader is expected to take further references to understand more. We use subscript I and j, each one of them take the value of 1, 2, 3, 1, 2, 3 corresponding to x, y direction respectively in Cartesian coordinate system. If the subscript is repeating in a particular term, then it is summation. If it is not repeating, then for each value you get single term. For example, if I write ui as one term, I subscript is repeating in both, then it becomes a summation. So, in this case, as I mentioned before, I takes a value of 1, 2, 3. So, you write ui very explicitly as u1 plus u2 plus u3. So, this is a short form of writing this quantity ui. If you write uj, if there is a term uj, then the subscript is not repeating, I takes a value independently 1, 2, 3 and j takes a value independently 1, 2, 3. So, we write a complete form for every I value, j will take value 1, 2, 3. So, we write here, so u1 which means I is 1, j is 1, u1 u2 which means I is 1, j is 2, u1 u3 which means I is 1 and j is 3. So, you can observe each term is independent. Similarly, I now takes the value of 2, j will take again the value of 1, 2, 3 separately. So, you get another 3 components u2 u1, u2 u2, u2 u3. Third possibility, I takes a value of 3 and j takes a value of 1, 2, 3. So, you have u3 u1, u3 u2 and u3 u3. So, you observe when you write a term ui uj, I takes a value independently 1, 2, 3 and for every value of I, j takes a value independently 1, 2, 3. In total you get 9 components. 9 independent component, and all the 9 independent components are displayed here. Now, you see immediately advantage of writing in tensor notation. To represent 9 independent components, it is so easy to write with the help of that subscript or index notation ui uj. We also learned that if this index is repeating, that index is called dummy index. If the index is not repeating, it is called free index. Now, what is the meaning of u1, u2, u3? We usually write x velocity as a u, y velocity as a v, and z velocity as a w. Instead of writing that way, we can also write u1 refers to x component, and u2 refers to y component, and u3 refers to z component of velocity. We are going to use one new term called Kronecker delta, which is given by the symbol delta with a subscript ij. Now, this Kronecker delta has a value of 1 if I equal to j, or 0 if I not equal to j, and this also is a matrix which is along the diagonal has a value 1 1 1. As I mentioned here, when I is equal to j, it takes a value of 1. So, you can observe this is delta 1 1, and this is delta 1 2 2, and this is delta 3 3. We will try to learn some more information about rules of averaging. Average of average is average itself. So, in this case u bar is average, and if you take a average of that u bar, that will be u bar itself. Average of fluctuation is 0. So, u prime is a fluctuation. If you take average, that will go to 0. So, fluctuation, it may be positive, it may be negative. If you take the average, it will go to 0. Average on the product of two fluctuation, however, is not 0. So, if you take u prime, which is a fluctuation for u velocity, v prime, which is a fluctuation for v velocity, and you have a product of these two fluctuation, and you apply a time averaging on top of it, they need not be 0. Average on the product of one averaged quantity and one fluctuating quantity is 0. Expression wise, u bar is a one average quantity and v prime is a fluctuation. You have a product of them, u bar v prime, and you take an average on that, that is equal to 0. Average on the product of one average quantity and one instantaneous quantity is a product of two average quantity. So, u is an instantaneous quantity, v bar is an average quantity, you multiply both of them, then you take an average, that will result in u bar and v bar. Average on the spatial derivative is the same as a spatial derivative on the average. That means, they are commutative in terms of expression. Dou f by dou x is a derivative, spatial derivative of the function f. After you perform the spatial derivative and you do average, that is the meaning of average on derivative. Spatial derivative is same as you take a derivative on the average. So, dou by dou x of f bar, average on the spatial derivative is same as spatial derivative on the average. So, they are commutative. I am only giving limited information about statistical way of dealing. These things will be extremely helpful when we go into the details of turbulent flow modeling. So, in today's class, I try to give information about what is turbulent flow with the help of illustration, some information about tensor algebra, index notation, and rules of averaging. Next class, we will go into the details about equations. Thank you.